Hi, I'm happy to share with you my fun journey exploring zero number in cryptography. I think like it's the funniest number in cryptography, and I hope that you will enjoy my journey. So the agenda is we will introduce a few terminology, and after that we will describe a high-level attack idea, for instance like zero signature or splitting zero attack. This talk is purely cryptographic talk, so it's technical. However, I like to get across the main ideas of the attack. So I want you to get attention in the first 10 minutes, and after that you can get back to sleep. For the rest of the talk, I will only describe the detail of the attack. But the high-level idea of the attack is simple, and I hope that I can get across those attack ideas. So let's introduce a few basic terminology that we will use in this talk. So the talk is about zero related bugs in both the standard graph and in all four crypto libraries that implement the standard graph, including ethereum, herumi, milagro, and supranational. So there are two types of bugs here that I will discuss. The first one is the implementation bug, where the libraries don't follow the security check that mandated by the standard. The second bug is the standard graph bug, and it's pretty serious because all four libraries will follow the standard, and as the consequence, all four of them will have the same bug. Okay, so this talk focus on signature verification. For the signer, will have the private key, which is denoted as lowercase x, and the public key is the uppercase X, and the message M. So we will not focus on the signing operation. Instead, we will focus on signature verification. Signature verification is pretty complicated in our case, but the high-level idea is pretty simple. Essentially, it's to check a certain function equals to 0. And our focus is the number 0, as we'll see shortly. So what's up with 0, right? Like in signature verification, essentially we check whether a certain function equals to 0. However, as you see, and you all know and love that, whenever you multiply number 0 with any number, you get back 0. It doesn't depend on the number at all. And this is how we will exploit this very naive property to attack crypto libraries and standard graph itself. Another concept that I'd like to introduce is called aggregate signature. If you've been working in traditional cryptography, you rarely seen this concept, but it's pretty popular in cryptocurrency because it has a very attractive property. Think about that you have to send millions of signature, and you have to verify millions of signature. So it costs bandwidth and it costs CPU time. Instead, in the aggregate signature scheme, we will have one single aggregator that will aggregate millions of signatures into one short signature, which in our case is only about 96 bytes. And the verifier, instead of verifying millions of signatures, is only verifying one single signature. So but like any new crypto construction has weaknesses, and it's not the topic of this talk. but we will try to exploit certain bugs in aggregate signature. As I mentioned above, the standard draft was aware of the danger of zero signature. Therefore, they request implementers to check zero signature and zero public key. This is as an attacker, we will try to bypass that check. So that's that one type of bug that we will discuss in details later. However, like the standard draft missed an important case where, even though each signature or public key is different from zero, their sum it might be zero, right? For instance, think about a very simple case when you have the first signature is 1 and the second signature is -1. Then the sum is 0. And you can still bypass the verification just by this very simple observation. Okay, now basically you can go back to sleep. The rest of the talk is more or less this slide, but it fill in the details like how it actually works from the mathematical point of view. There will be some demos, but if you can understand this slide, then I'm already really happy. Okay, so elliptic curve. I will have only 30 seconds to introduce elliptic curve. So the elliptic curve, as you can see, is the blue lines on the graph. And to add 2 points P and Q, we draw lines through the points P and Q, and it will cut the elliptic curve at another point R prime. But that point is not a sum of P and Q. Instead, is the negative is the sum of P and Q. For the purpose of this talk, we're not going to discuss how the addition is computed or like complicated math. All we need to know is addition operations. So essentially you can think of elliptic curve somehow magically define the addition operation, and it has a 0 point. The nice thing about 0 point is whenever you add 0 point to any point P, then you will get back the point P. In our case, we defined and we fix a base point G on the generator, and when we add G together n times, then we will get back 0, and n is called the order of the point. Essentially, all we need to remember is elliptic curve defines the addition operation, and it defines the 0 point. We don't need anything else more complicated than that. All right. So another concept that we will talk about is called pairing. So pairing is essentially just a maps from 2 points P and Q to a number. Technically, it's a maps from 2 groups to a finite field. But for the purpose of this talk, that technical details is not important. What we need to remember is it maps 2 points to a number, and that's it. So pairing has a few nice property, which is called bilinear property, that we will use over and over again whenever you look at pairing-based cryptography. So the first property is if you add 2 points on the left-hand side, and on the right-hand side, you will have the product of pairings. And the second property is pairing of A times B, P, and B times Q equals to pairing of P and Q to the power of A times B. What it means is you can move the coefficient of the points to the exponent. And if you look from the right to the left, it means that you can move the exponent to the coefficient of the point. And using this property, you can see that pairing of AB and BQ equals to pairing of BP and AQ. And we will use this property over and over again. In our case, pay attention to the edge case that I stressed there. Basically, the pairing of 0 point and arbitrary point is 1, no matter what that point is. So we will basically exploit this observation for our attack. One of the simplest yet elegant application of pairing is BLS signature. The way it works is simple. To compute the signature of a message M, all we do is to hash the message M to a point on the curve, and we multiply by a number X. And that's it. You can't find a simpler signature than that. So how do we verify BLS signature? Basically, to verify the BLS signature, we will compute 2 pairing. The first one is the pairing of the signature and the base point G, and on the right hand side is the pairing of the hash and the public key X. So why does it work? So if you look at the equation, you can see that the signature is X times hash, right? And you can move the coefficient X to the exponent. So you move X to the exponent, and then you move X to the right component of the pairing, and it's actually just the public key. All right, so for the purpose of this talk, we'll pay attention again on the 0 signature and 0 public key. So in that edge case, the pairing of the signature with the base point always equals to 0, and the pairing of the message with 0 public key also equals to 0. What it means is the signature is valid for all messages. And this has a lot of advantage from the attacker point of view, because whenever the verifier verifies the signature, the verifier learns nothing. From the verifier point of view, whenever you verify the signature, you want to learn something, that what message has been signed. But in this case, before and after verification, there is no difference. The standard graph was aware of this issue. That's why it asked all the implementation to check for 0. However, let's see whether we can bypass the check in practice. So I need to describe to you a little bit more details how the points and byte array representation of the point. So in the software, there is no thing called point, right? Everything is byte. So, but however, there is multiple byte arrays that map to the same point, and that is fine from the signature perspective. What Ethereum elliptical library does is it only checks the canonical representation of the point, and it doesn't check all the other byte arrays. So as an attacker, what we do is very simple. We just need to find a different byte array presentation of that point, and then Ethereum elliptical library will just accept it. I have a short demo here. So in this case, we have a 0 public key, and this is the canonical presentation. We have 0 signature, and then we will generate a random message, and the verify will return true, as you will see shortly. Okay, So let's continue to BLS aggregate signature. So in the past, BLS signature is attractive because it's short. However, because of advanced cryptanalysis, cryptography has to increase security parameters, so it's not short anymore. However, BLS signature has an attractive property. It allows signature aggregation. So the idea is, instead of verifying millions of signatures, we will have an aggregator that will aggregate all of them into one signature, and then we will only verify that signature. That sounds magic, right? But it works. And in our cases, the verification is to compute some pairing. On the left-hand side, we compute a pairing of the signature and the base point. And the right-hand side is the product of pairing of hash and the public keys. So how does it work? Basically, it will use the property that we mentioned in the pairing section. The first equation, we only write the definition of signature, right? It's the sum of two signatures. And in the second and third equation, we move the coefficient from the left component to the right component. And essentially, the private key times G is just the public key. So in the special case, when all the messages equal to each other, then we will have a very fast algorithm, and it's called fast aggregate verify. Basically, because all the messages equal to each other, their hash equal to each other. And as you can see from the equation, instead of computing two pairing, we will only compute one pairing with the aggregation of the public key. Pay attention to the aggregation of a public key, because this is exactly where we will exploit. So in this case, the standard is correct, but all the a few implementations such as milagro and herumi is not correct. Basically, the library checks for zero public key, but it only checks single public key. It doesn't check the aggregate public key. But as an attacker, we can create public keys so that their sum is zero, and we also use zero signature. As you can see, the pairing of zero signature and the base point is 1, and the pairing of the hash and the public key is also 1. Yes. So what it means is the aggregate signature is valid for all messages, and it's the same attack. It's just that in this case, we split 0 into multiple parts. Each part is different from 0, but their sum is 0, so that we can bypass the verification check. I will have a small demo here for milagro BLS library. So we will create two keys whose sum is 0, and then we will send the 0 signatures. So this is the canonical presentation of the signature, and then we'll generate a random message, and fast aggregate verify will return true as well. Now let's move on to a bug in the standard draft itself. So this is the general case when the message might not equal to each other. On the left hand side, you have the pairing of the aggregate signature with the base point G. On the right hand side is the product of pairing between hash of the message and public key. So the standard craft underestimates this case, and so it's vulnerable to the splitting zero attack. And all libraries, including Ethereum, Milagro, supranational blst, or herumi, are vulnerable because they all follow the standard. So this is a very important point, and I want to stress that when cryptographers write, scientific papers, maybe no one actually read your papers, but when you write standard, even if it's just a draft, people will follow your standard. And if you're not careful and you don't treat the standard seriously, then the consequence is disaster, because everyone will implement your vulnerable standard. So in the general case, I will describe the splitting zero attack against the standard and all libraries. So in this, there are two types of attack vector here. On the left hand side, you can see that if a signature is valid for a message M, and then it's also valid for a different set of message. In our case, it's valid for M1 and M and M. For all M, it doesn't depend on M at all. As we can see in the demo that I will show later, the attacker doesn't even need to sign the message M at all, because the verifier actually never verifies single signature. All the verifier verifies is the aggregate signature. And the second attack vector is on the right hand side, is if sigma is a valid signature for M1 and M2, then it's also a valid signature for M1, M3, for all M3. It doesn't depend on the message M3 at all. Okay, so I will show you a short demo about splitting zero attack against supranational blst library and standard craft. So here we have the user published signature sigma 3, and the attacker will create two keys so that their sum is 0 and the signature will be valid for a completely different set. As you can see that we will create an arbitrary message, and then we will print out the result of aggregate signature verified. In the screen, you can see that result is true. But it's not the end of the story yet. The standard even have a mathematical mistake. So basically, a very simple requirement is it must be correct, right? What it means is when you use two equivalent interface, then it must return the same result. It's a very basic correctness requirements. However, the standard craft has a bug which will return completely two different results, even for the same input. And it caused consensus bug. A few clarification on the consensus bug means here. Consensus here only means that when you have one data and signature, but you have multiple interpretations of the same data and signature. It doesn't mean consensus in the sense of the blockchain technology. And here I will show you a demo that two equivalent interfaces will return different results for the same data and signature. Basically, we'll have two keys whose sum is 0, and then we will use two API. One is fast aggregate verify and the other is aggregate verify. As you can see in the screen, one return false and the other return true. Okay, so to wrap up, why splitting zero attack is dangerous? What makes it special, right? For the aggregate signature case, the attacker private key are completely randomized, even though their sum is zero. But from the outsider perspective, they don't know x1 and x2. What it means is the attacker fully protects its private key and the attack cost is free, which is very different from the single signature case where the attacker leaks its private key. From the defender point of view, detecting colluded key is very challenging because it's equivalent to finding solution to a very hard problem, which I think no one knows how to solve. And finally, for the aggregate signature, the verifier only verifies the aggregate signature. It never sees single signature at all. And so it never verifies single signatures. And so the verifier will never be sure what happened in the past. And it leads to different kinds of attack at the application layers. Thanks for your attention. I hope that you enjoy the zero key and appreciate the number zero in cryptography, because I think like this zero number has been ignored in the past, but in the different context for aggregate signature, its role becomes important and we should pay attention to it. Thank you.